Most Kubernetes dashboards got it wrong. Most did not understand the limitations of Kubernetes API, and as a result of that, act in a similar way as glorified file explorers, rather than tools that help us find what we're looking for, especially when dealing with large scale. Today we are going to explore the mistakes Kubernetes dashboards are making and try to figure out how they might be able to get onto the right path, even though that might require some drastic changes in their design. By the end of today's story, you should see what we need to navigate, search, and debug, and do whatever we might need to do in Kubernetes clusters. We will feel like we are using Google search rather than navigating through Kubernetes resources in a similar way we are traversing files and directories. Welcome to DevOps Toolkit, the channel where we prefer searching for answers rather than navigating through files and directories. Most Kubernetes dashboards are more or less the same. Most assume that they should be doing the same job as file explorers. They allow us to list files and directories, navigate from one to another, and get information about any of them. Let's take a quick break to introduce you to Twingate, the sponsor of this video. Now, let me ask you something. Are you tired of using VPNs, but you still want to work securely? If you are, this might be the time to ditch, remove, get rid of VPNs. I mean, they're evil, right? And to switch to Twingate. It is a VPN replacement. Now, when I say VPN replacement, I don't mean the kind of VPN that allows you to watch Netflix or the kind of VPN that allows you to access your bank account. I mean the kind of VPN that allows you to access your network, your infrastructure, devices, home lab, or anything else related to your work. And the best part is that it is not a VPN. It is not one of those that end up preventing you from working or making your internet connection feel like you're using a modem from 90s. It's easy to set up and it's fast, like really fast. There is a free tier, try it out, get rid of VPNs. Thank you Twingate for sponsoring this video, and now let's go back to the main subject. Most Kubernetes dashboards act in more or less the same way. Here's Headlamp. It's a Kubernetes dashboard similar to most other Kubernetes dashboards. Now, before we proceed, I have two important notes. First, today's video is not about Headlamp. It's about something else, and I'm using Headlamp only to demonstrate some of the issues Kubernetes dashboards are facing. Second, I might be negative towards dashboards, and you might interpret that as me being negative towards Headlamp. I'm not. I think that Headlamp is one of the best, if not the best, Kubernetes dashboard. I'm negative towards typical implementations of dashboards. It's a general negativity that is not aimed specifically towards Headlamp. If you open Headlamp, we are presented with the same functionality and information as any other Kubernetes dashboards. It starts at the cluster level with information like CPU and memory usage, number of nodes, and so on and so forth. We can think of a cluster as a root directory of a file system. If you select workloads, we can see all Kubernetes resources that ultimately manage containers. There are pods, deployments, stateful sets, and others. Think of them as directories nested inside each other. So we can see information about any of them. We can also see which resources are managed by, in this case, the deployment, just as we could see files inside the directory. So think of a dashboard as a file explorer. We can start at root, a cluster, and navigate through different types of resources just as we would be navigating through directories. Eventually, we will find what we're looking for and get information about that something, whatever it is. So, Kubernetes dashboards are conceptually similar to file explorers. If you're old enough, you might remember Yahoo, which had the same approach. It tried to organize the internet into categories and subcategories, and we would be navigating through it in a very similar way as we are navigating through a file system. That failed miserably. And the reason for that failure is obvious. You cannot organize something as massive as internet into categories and subcategories. The only reasonable way to find something across whole internet is to search for it. That's why today we have Google, and most people do not even know that Yahoo existed. Google is a household name today, while Yahoo abandoned most of what it was doing and is now limited to some obscure services. You see, we can have one or a few hundred clusters, and each of them can have dozens or hundreds or thousands of resources that are constantly moving around. New ones are created and existing ones are being destroyed or mutating all the time. It's a lot. Now, to be clear, it is sometimes useful to navigate through it all by choosing a cluster and then going through namespaces and resources until we find what we're looking for. However, very often that's not what we really want. We often want to find what we are looking for by searching for it. We should be able to ask a question like, give me all resources that belong to this application no matter in which cluster they are located. Or give me all pods that are not working no matter where they are. Or any other similar type of a query. However, dashboards cannot do that. Not necessarily because they don't want to, but rather because they can not search. Mainly because they rely on Kubernetes API to give them the information. Let me explain. Kubernetes dashboards are first and foremost a way to provide graphical representation of data provided by Kubernetes API. So, any advantages as well as disadvantages of the API are automatically advantages and disadvantages of dashboards. Here's how it works. We have a Kubernetes cluster that is accessible through its API. When it comes to getting information from it, we ask it, in this case through a dashboard, to retrieve information of a specific resource. We can ask it to give us everything it knows about any resource. To get that information, we need to ask for a specific kind of a resource in a specific namespace and with specific name. The problem is that we need to know what exactly we are looking for. Fortunately, we can also ask it to give us information about all the resources of a specific kind in a specific namespace, or even across the whole cluster. We can also filter resources based on labels. But that's about it. The problem is that querying capabilities of Kubernetes API are very, very limited, even though it might not seem that way. We cannot search across all the resources. There is an alias all that is misleading, since kubectl get all actually retrieves only specific resources, which are often a fraction of the resource types we might have in a cluster. We cannot search by image, by status, by keywords, other than labels, and so on and so forth. We cannot, for example, ask Kubernetes API to give us all resources, no matter the type, that contain a keyword in the name. There are no expressions like those commonly used in, let's say, SQL databases. The reason for those and many other limitations lies in Kubernetes internal database. Kubernetes API is essentially an interface that allows us to interact with etcd, its internal database. It's a key value store that is not meant to be used as a database we can query. Its primary function within Kubernetes is not to serve as a traditional database we can query, but rather as a system of record. Its primary purpose is to be a reliable storage for the state of all resources managed by Kubernetes. So any question we send to Kubernetes API is being sent as a query to etcd, and the result is returned back to us. Kubernetes API is, in a way, front-end with etcd as a backend. If a query is not allowed by etcd, it is not allowed in Kubernetes API. Now, part of those limitations are somehow overcome by making multiple requests to the API. If we would, for example, like to list all the resources in a Kubernetes cluster, we would first need to make a query to retrieve all the resource types. That would be one query. Now, let's say that there are 100 resource types in a cluster. To get them all, we would need to send additional 100 requests to the cluster. That would be 101 request only to list resources managed by the cluster. From there on, if you would like to filter those resources, the interface we are using, a dashboard in this case, would need to process those resources internally so that only those we are interested in are displayed. Now, if you would like to search for a specific keyword in those resources, we would need to make another trip to the API for each of the returned resources to get all the information about each of them and do some internal filtering to find out whether that keyword is indeed present somewhere inside the data that belongs to each of those resources. So let's say that there are 10,000 resources in total. That would be another 10,000 requests to the API, totaling so far 10,101 requests on top of internal processing that dashboards would need to make. Now, to make things even more complicated, let's say that we have 12 clusters. If that search would be performed across all those clusters, that would be 10,101 requests multiplied by 12, resulting in 121,212 requests, only to get raw information that still needs to be processed by the dashboard. Such operations would be very, very slow at best. If we would perform them more frequently, we might even crash etcd instances in those clusters, and that is not something we would like. That's why most dashboards are showing data as tree-like structures, allowing us to traverse the cluster in pretty similar way we are navigating through files and directories on a computer. That's why most dashboards do not show us all the clusters as a single unified view, but force us to navigate through one cluster at a time. That's why dashboards rarely have an option to search for resources, and even when they do have that capability or those capabilities, they are very limited. The root cause of those problems is that in this scenario we would be trying to use etcd through the API for something that is not designed to be. etcd's main purpose is to be a reliable system of record, not a searchable database. It intentionally limits querying capabilities. If we would like to be able to perform real searches based on data in Kubernetes, we would need to replace etcd with some other type of database like PostgreSQL or Elasticsearch or anything else that has better query capabilities. However, that would be a bad idea as well. To begin with, replacing etcd is not trivial and is likely to jeopardize one functionality for another. We would be putting reliability and speed in danger for the sake of search. In case of Kubernetes, having a reliable system of record is more important than being able to perform free text search. On top of that, we would still not solve the problem of searching across multiple clusters, since we would still need to make as many queries as there are clusters. A much better solution is not to replace etcd, but instead to add a database that synchronizes data from etcd instances from all the clusters into a central location. If we do that, if we manage to have a central database where all the data from Kubernetes clusters is synchronized, our dashboard could stop asking Kubernetes API for information and instead perform queries against that database. If we do that, we would transform our Kubernetes dashboard from allowing us to navigate through clusters, namespaces, and resources to acting in a similar way as Google is acting for internet. We would be able to search for anything using any criteria we deem important. We should be able to find almost anything almost instantly. If we do that right, we could actually have both. We could have a traditional dashboard that allows us to choose a cluster, select a namespace, see deployments in it, find replica sets it created, and drop into pods managed by one of those replica sets. That would be the mode where the dashboard is sending requests to Kubernetes API. Then we could combine that with a search that will allow us to find anything we want as long as we know what to search for. That search would not be limited to a single cluster, a single namespace, a single resource, or a set of labels, but find information no matter what it is and where it originates from. As an additional bonus, if all our data is stored in a central database, we might be able to extend capabilities to, let's say, AI. We should at least, in theory, be able to point an AI model to that database and start asking it questions. Now, let's take a look at one such solution. Today we'll use a project called Karpor, which is a part of Fusion Stack. You might want to explore other projects from the stack. They're all very interesting. You'll have to do that on your own though, since Karpor is the only one that matters within the scope of today's subject. So let's start by port forwarding Karpor service and opening it in a browser. Karpor's home screen is frankly boring, just as in a way Google search home screen is boring. In both cases, the only prominent thing is the search field. We'll get to it later. Right now, we should register our clusters. Here it goes. Add cluster.o2, upload kubeconfig, click verify and submit. Do the same for the second cluster, repeat the process for the third, and there we go. The 3 clusters I prepared for this demo are added to Karpor. If we go inside one of the clusters, we can see the same boring info that we can see in any, and I repeat, any dashboard. There are statistics, like the number of nodes, CPU and memory utilization, the number of pods, and so on and so forth. We can also see the issues related to that cluster. Topology is semi-special, let's say. Unlike other dashboards that might show us network traffic in a similar view, Karpor shows us how our resources related to each other. That might be something semi-complex to do in other solutions, but in case of Karpor, it is trivial because it does not get the information from Kubernetes directly, but from its internal database. We'll get to that later. Finally, we can also get all the pods running in that cluster. All that is boring, and to be honest, if that would be the main feature of Karpor, I would not waste a single second on it. That's not the case though. Cluster management is the part of Karpor that exists in any other Kubernetes dashboard-like solution. So we'll just move on back to the home screen. Search is what makes Karpor special. And we can see from the tooltip in the search field that it is based on SQL. That's awesome. Not because SQL is the best query language, but rather because it is something that almost everyone knows. There is hardly any software engineer that does not know at least basic SQL. Even if you find such a person, it takes no time to learn it. So, what can we do with that search? We can, for example, query all resources with the name set to silly demo. And there we go. We can see the list of all the resources with the name set to silly demo. Now, pay attention since those are a couple of important notes here, which you might have missed. First of all, we got results from all three clusters. We can see that by cluster values. If we had 100 clusters instead, we would get results from all those as well. All in all, we got all the resources with the matching name, no matter which cluster or namespace they belong to, and no matter which resource kind we have in the cluster. Even though today's demo has only standard resources, we would see custom resources in the output if we had any. The second observation is that we got the result almost instantly. It was blazing fast. If we tried to get all resources, no matter the type, from a single cluster by querying the API directly, it would probably take more time, given that it would need to send quite a few requests to accomplish the same result. If we take into the account the fact that we got results from multiple clusters, querying the API directly would take even more time. We can see that we got services and deployments. We can see that replica sets, pods, and potentially other resources are missing. The explanation for that behavior is simple. When a deployment creates a replica set, it generates a name that starts the same as the name of the deployment and ends with some non-deterministic value. The same happens with pods created by replica sets. As a result, those are not, in this case, named silly demo, but silly demo followed with some hash string. As a result, those were not returned since their names do not match what we asked for. A potentially better way to get all the resources we want, even though auto-generated, could be to query by a label. This time we got more resources. There are now replica sets and pods as well. Now, searching by labels might not work for everyone since that would mean that we know which labels are used. So let's try to get the same result by searching by name again. But this time, however, we will try to find all the resources with the name that contains word silly. Since we are using a standard SQL, we can accomplish that through the like instruction by typing where name like silly surrounded with percentage signs. We got the same result as before, but this time with an arguably easier syntax that at the same time does not force us to know the labels. Next, let's say that we would like to sort the results by timestamp from newest to oldest, and still unrestricted by any type of the resource. We can do that by adding order by creation timestamp to the previous query. Now we got again the same results, but this time sorted. The best part of it is that we did not have to learn almost anything, but just type standard SQL queries. It's brilliant. Now, let's make it more interesting by saying that we would like to find resources with the image silly demo and tag 14327, and further on, let's say that we don't know what is the specific field that should contain that information. And to make it even more complicated, let's say that we do not even know the full image, but only that it contains silly demo : 14327. We can do that by simply specifying the where statement that it should contain content that has silly demo 14327. In other words, we are saying find resources that contain that value somewhere. We have no idea what those resources are, nor where that value is, nor what the full value is. Just find anything that contains that string. And look at that. We found 2 deployments. And that's awesome. Similarly, let's say that we would like to find all the resources that are somehow, without knowing how, related to production. The only assumption we'll make is that they have the word production mentioned somewhere, be it a label, an environment variable, image tag, or anything else. We can do that with a query similar to the previous one by simply instructing it to find resources that contain the word production. And there we go. We got all the resources of any type and from any of the clusters, and that contain the word production. That's amazing, right? We can also observe that 2 of the pods have the status image pool backoff. We stumbled upon an issue that we want to resolve. We can see that it affects only pods, that it is limited to the production namespace, and that they are all related to silly demo resources. Let's narrow it down by typing another query that will get resources that contain the name silly that are in the namespace production and from any of the clusters and with the kind pod. We got 2 results. We found what we're looking for, so we might want to take a look at the details. Some of the things you see on the screen are pretty standard on all dashboards. What makes this different is mainly how we got where we are, rather than what we are seeing. We have the list of potential issues and we could get that from some other solution as well. It's nothing new. Topology is somewhat special since it shows all the resources directly or indirectly related to the pod we are observing. We can see that it was created by a specific replica set, which was created by a specific deployment. We can also observe the service related to it and the node where it's running. While all that might not seem special at first, that's actually something non-trivial to gather by other dashboard tools that would need to make multiple trips to the API to gather all the information and stitch it all together. Still, that is not the main feature and certainly not something that hasn't been seen in other tools. How to get here is what makes it special. Search is the star of the show. There's one more interesting feature we should explore. By default, there is only one insight available. It shows us all the namespaces. Since the data is coming from a database and not a specific cluster, that is the list of all the namespaces across all the clusters. While that might be interesting, it's not very special by itself. But we can make it special by adding our own insights. Let's create one. We'll type app as the name, select labels as group by, type app Kubernetes IO/name as the value next to it and click the submit button. Now we can select the app tab. We can see all the resources from all the clusters grouped by the label name. In other words, now we can see all the distinct apps. That is yet another operation that would be very expensive if the dashboard would need to query all the clusters to find all the resources and then discard those that do not have that label and finally group them all. Since Karpor is not working with Kubernetes APIs directly, but with data in a database, that operation was simple and fast. Let's make another one, just for good taste. We'll type team as the name, select labels as group by, type team as the value next to it, click the submit button. And now we can see all the teams using the cluster, assuming that their resources have the matching label. Let's select the A team, and over there we can see a similar page we saw before, but this time only with resources that have the team label set to A team. As always, data is coming from all the clusters. And now comes the exciting part, even though you will be disappointed later. And that part is AI. As I already mentioned, it would be complicated, maybe not even possible to introduce an AI model that uses data from all the clusters, since such data would be difficult to extract from the API. Karpor should not have a problem with that, since all the data is available in a database. As such, we can go back to the home screen and use the search field to ask a question to one of the AI models. Now, we will not explore that today, mainly because AI is not yet fully baked in. It's not yet working as expected, but hopefully it will soon. And I'm really looking forward to it. Actually, it's more than that. I can't wait for it. As a recap, summary, traditional Kubernetes dashboards fetch data from Kubernetes API. If you have multiple clusters, they're fetching data from all of them, but only when we request it. More often than not, dashboards operate on a single cluster. We can switch from one to another, but we will be observing a single cluster at a time. The approach we discussed today is different. There is a database, which in case of Karpor is Elasticsearch, but it could be anything else. On top of that, there is a process in the control plane cluster, as is the case with Karpor, or one in each of the clusters. Those processes are reacting to Kubernetes events and synchronizing data into the database. As a result, when we request some information from the dashboard, it can forward that request to the database and send the output back to us. We get quite a few benefits from that. First of all, we can query data by almost any criteria we want, without being limited to the capabilities of Kube API. Second, we are not limited to a single cluster, since all the data is gathered in a single place, the database. Finally, all that opens the doors for some potentially very interesting integration with AI. Even though Karpor did not yet finish such integration, it should be able to instruct the model to fetch that same data gathered from all the clusters when trying to answer our questions. As such, I'm much more positive about potential AI integration than if we would hook a model into a traditional dashboard or Kube API. Here's the question though. Does all that mean that you should replace your favorite Kubernetes dashboard with Karpor? And the answer to that one is a huge no. Don't do it, at least not just yet. While traditional dashboards lack search and processing capabilities Karpor offers, they are good at everything else. Now, if we modify the question to be, should you look forward to using a similar solution in the future, the answer is, I hope so. Karpor is not the first tool to take this approach. There are others that realize that if we want to find out what's going on in a fleet of clusters, or even a single cluster, we need to sync data into a database and query it instead of querying etcd through Kube API. Karpor, however, is missing the baseline features of a dashboard. Will it get it? I don't know. I'm not sure. And here's what I would really like to get. I would like maintainers of a dashboard like, for example, Headlamp, to join forces with Karpor and integrate its capabilities. If we would have Headlamp or any other similar dashboard with search and filtering similar to, if not copied from, Karpor, we would get something amazing. And that's not even that hard, since Headlamp can be extended through plugins. It's doable, I just need someone to do it. And if that happens, we would get a dashboard better than any, and I repeat, any other. Thank you for watching, see you in the next one, cheers.